Okay. Hey guys, we need to focus. We have a lot to do today. Rotic geometric sequences or infinite rotic sequences, geometric sequences, or infinite geometric series, because series are adding. Any questions on those problem sets, like the kind of the standard nuts and bolts, simple, I think, straightforward questions. Any question on these at all? The answers were provided in your worksheets. No, okay. Oh, okay. Then let's do the crazy ones. How these problems here? Which one do you want to talk? I did provide the worked out solutions, but I can still talk about it if you're still stuck.
Yeah.
Any of these you want to talk about? Which one? 3 and 4? Okay, we'll see 3 and 4. Okay, for number 3, you're told that x4y follow a successive term in a rotic sequence. x3y follow a pattern of geometric, right? So find 1 over x plus 1 over y. So what you want to recognize that common differences happen for rotic sequences. So 4 minus x must equal y minus 4. Right? If I do the second term minus the first term, those equal the third term minus the second term. And if you want to isolate y, go ahead. Y would equal 8 minus x. So we're okay with that. Okay, next up. This would be a constant ratio. So 3 over x must equal y over 3. Again, if I divide the second by the first term, it must be the same thing as the third term divided by the second term. Does that make sense? So y must equal 9 over x. Now, what do you think I'd do next?
XY.
Yeah, it's substitute, right? Correct, right. So, so 8x minus x squared equals 9. 0 equals x squared minus 8x plus 9. So did I do that right? Someone seems off. Hold on.
I think the way you ended up doing your answers, the way that I didn't figure out.
Hold on. Oh, it's gonna require a quad form. I want to avoid.
You can rewrite 1 over x,
Oh.
1 over y into x plus y over xy.
Yeah, I see what you're saying.
And then you can just...
So hold on a second. You're saying I could rewrite 9 over x as 1 over x equals y over 9?
Rewrite 9 over x as xy equals 9.
Okay.
And then you can rewrite 8 minus x equals y as x plus y equals 8.
Okay.
And then you can say I'm looking for you're looking for 1 over x plus 1 over y, but I think that's just the same as x plus y over xy. You have both of them.
Oh, I see what you're saying. Okay. Let's back up a little bit here. No, I follow you, Sean. I follow you. Okay. I don't know. Okay, so far I think what I did. Okay, I know what you're talking about now. Yeah, no, I see it, but a lot of people don't see it. Okay. Whoa. But thanks, Sean. Here's the deal. So far this makes sense, right?
Yeah.
So far this makes sense. The problem is, right, why I stumbled is because this would require a quad form, because I can't think of 2 integers that multiply 9 add to -8. I can do -1 and 9, but that multiplies -9, right? Or sorry, 1 and -9. But still, it's not gonna be okay. So you can do quad form, get these nasty answers, get nasty answers for y, then do 1 over a nasty answer plus 1 over another nasty answer. I don't know if that's really wise, but remember, we're not asked to solve for x and y directly or individually. Just ask for the values of this expression. So if I were to combine these two fractions, the LCD is xy, right? So would you agree after I combine I would get this? But multiplies by y and y, and that by x and x. We're okay with that? Okay. Well, to Sean's point, that's very clever, Sean. What's x plus y equal to? 8. What's xy equal to? 9. So that's the final answer. 8, 9, there you go. Now, if I did do quad form and got these nasty answers and solve for y afterwards and then did all that stuff up there, I would get this by simplifying correctly. It just would have been a real pain to do. This was so much cleaner and nicer. So thank you, Sean, for bringing that up. So yeah, that's the best way to do it. And hopefully I did that way in the answer key. I'm pretty sure I did. No, I did not. Oh, I did do the nasty way, didn't I? Oh goodness. It wasn't too bad. Okay. But you get the idea. You could do it this way, and it does come out that way. But yeah, that was much cleaner what Sean suggested. So anyway, so we're good on that one. You guys want to go over 4? Yes or no? Yes, okay. We'll go over 4, and then we'll move on to the notes for today. 3 different numbers whose product is 125 are 3 consecutive terms in a sequence. Geometric sequence, great. At the same time, they are the first, third, and sixth terms. Ooh, that's interesting. Okay. So if you think about it, the first number we'll call it x, right? What will be the next number in the geometric pattern? Call it xr, right? Because you have to multiply by r. And what would the next term be? Xr squared, right? So if I were to multiply all of it out, I would get x cubed, r cubed equals 125. Right? Because they said the product of all those multiplies 125. And if I cube root both sides, what does xr equal? Okay. So far we're okay. I think that's probably best I could do so far with that. Then at the same time, the first, third, and sixth terms, sorry, they represent that. Okay. So wouldn't xr minus x equal twice the common difference? You guys agree with that? The third term minus the first term is twice the common difference? Because you have to apply a common difference 2 times to get from the first to the third term. We're okay with that? And wouldn't you agree that xr squared minus xr would equal 3d? Right? Because no, x is the first term. X was the second term because you have to multiply by r to get to the second term. It was geometric, right? And then xr squared to get to the third term. And then that one should make sense, hopefully, as well. You could do some substitution. Again, I might lean on Sean. Sean, do you have a more clever way of doing this one or no? All right,
You still have to you still get those ones.
All right, okay. So we're just gonna go by brute force. If someone sees something more creative, please share. But why do I love these? Because they're crazy. I love crazy. And also, sometimes they will spawn some creativity. Okay, so if I get d by itself in each situation, I get that, right? I get xr minus x over 2 equals d. Xr squared minus xr over 3 also equals d. Now this is where, I'm going to get a little creative here. What does xr equal? 5, okay. So couldn't I just say this? That 5 minus x over 2 equals d. Okay. And can I also say d equals xr squared minus 5 over 3 also equals d. I'm sorry, repeat that again. Actually 5 times r, right? Let's because xr squared is xr times r. So I'd agree with you. Yep. Give me a sec here. All right. Now I got 3 variables and 2 equations, so now I'm a little stuck. Give me a sec. I could also say this as well. Xr squared minus x equals 5d. You guys agree with that too? That's because the first and sixth terms is 5 times common difference. So I could also say this as well. And I could also rewrite it as 5r
minus x over 5 equals d. Okay. So I can then do a couple more. Okay, I feel there's a much easier way of doing this one. I'll look my answer key in a moment because I know how it worked out. And Sean, just hold on. I know you're gonna tell me something better.
It's not great, it's still kind of gross.
Okay. Well, let's set those equal to each other, right? So be persistent. Okay. Even though I don't know the next step, it's okay. Just be persistent. What happens to the twos? They cancel out. Crap. Right. They'll cross multiply. See, that happens. That's why we do this as a team. So 10r minus 10. You could say 10r plus 3x equals 25. I could also set the bottom two equal to each other. So 5r minus 5 over 3 equals 5r minus x over 5. 25r minus 25 equals 15r minus 3x. This is getting pretty ridiculous. If I move things around again, I'm spinning my wheels because I'll get dependent equations. Shoot, what did I do wrong? Or what am I not seeing here? I'm not doing anything wrong necessarily. Okay, I'm gonna look at my answer key. So now I'm gonna cheat. I know. Sorry, guys. A little disappointing. I did get the answer. Okay. I was correct. Okay, so x equals 5r. I wonder why I did that. Y minus x equals 2d. Okay. Okay, that works too. Okay. All right, had all that. All right. All right. I wonder why I was spinning my wheels. Have this, okay. And then I substitute for d. Oh, isn't that interesting? Okay. I should just point to the answer key. I won't waste your time like that. I apologize. Because I probably worked this many times. So does that make sense how I
Everything I was doing was fine so far. But the one thing I kind of did was I replaced x with 5 over r. And then got d by itself in each case. So I think what I should have done, my fault, I should have eliminated a variable. Because I have too many variables, 3 variables in 2 equations. That's crazy, right? That's why we spin our wheels. And I just spun them. You saw that about a minute ago in a very lovely way. So what I do is replace x with 5 over r, and then replace d, and then you get one equation in terms of r. And then you can use plot form to solve it.
or factor? Okay. And once you solve for r, you get x, y, z. So there you go. No, I won't do this on a test. This is a little too much, I feel.
Why do you cross out one as an option for all? Like if you.
One.
If you multiply by 1 each time.
It's
Yeah, but it's still a sequence.
yeah, but it's not gonna get us. I don't think it's gonna get us 125 though.
Yeah, well, it's just five cubed, right?
Hold on. Your common difference would be
Common difference would be 0. R is just 1.
what did the instructions say?
It's like 1 actually.
Well, no, it could still work. Hold on.
The first, third, and sixth.
It says 3 different numbers. I think that's
So it's
why.
gotta be.
You say 3
It
different?
does say 3.
Then there you go. So yeah. Yep. Then there you go. That's why. Okay. Whew, that was a crazy one. All right, let's move on to new stuff today. All right.
We got new stuff to do. Or is Norcus teach me on Friday? Prior here. Okay, for those who do notes electronically, just go to Schoology to get the notes. The rest of you guys, I'll have the notes and the homework right now. We're gonna start taking a calculus approach to sequences or looking at limits of sequences. What are you logging at? Oh, sorry. One, and the homeworks, we're gonna get that out of the way. Back over there. All right, so let me cue up the notes here. Here we go. Okay, there's a lot of words here. Don't worry so much about the words. But we are going to talk about what is an infinite sequence of series. We'll talk about the difference between a sequence and a series. Sequence, as I think I already mentioned, is just a list of numbers. A series, when we add up those lists of numbers. Infinite means goes on forever. You could find the limit of a sequence, meaning if you're trying to find the 100th or 1000th term, eventually it's going to settle on a certain number. We'll talk about that. And that's an idea called convergence. If it doesn't, then we say it diverges, because diverge means you split. Converge means you come together. For those who are taking physics, if you guys learn about lenses, convergent, divergent lenses, no, not gonna worry about it. It's all good. What was that? Yeah, there we go. Yeah, you know what I'm talking about. Yeah, there you go. Okay. Anyway, and the definition of a sequence is something that follows a particular pattern, right? As we know. So, and we will tell us each term, Thomas, thanks. We tend to list each term as A1, A2, A3. So the first, second, third term. We'll typically let n equal a positive integer. And again, it should be intuitive. A1 is the first term, A10 will be the 10th term, A20 will be the 20th term, and so forth. A sub n is a general way of writing the nth term. And if you see ... afterwards, that means it's going on forever. I'm not going to talk so much about them lying on a plane. So let's just kind of jump to the first example. Okay, let's look at the first example, right? The 100th term of a sequence. A sub n equals -1 raised to the n power over n squared plus 1. So if you want to find the 100th term, that's not hard. Just plug in 100 for n, right? There you go. Now, if you raise -1 to the 100th power, what happens if you raise -1 to an even exponent? It's always going to be 1, right? Any negative number will be positive when you raise to an even exponent. 100 squared, that's 4 zeros, so 10,000 plus 1. There you go. So that's your 100th term. Now, if you think about it, ultimately, if I plug in infinity for n, or just a crazy big number for n, like say 1,000,000 for n, right? What do you think the sequence is going to eventually converge to or settle on? Eventually 0. Now, will it alternate between being positive and negative? Sure, it will. But at the end of the day, it's going to settle towards 0. It'll be like -0.001, 0.001, -0.00, like, and so forth, right? And actually, I think I know why the graph was shown on the previous page. I think now I get it. What if you let n be your input, right? Let's say a sub n is your output. So n's like x, a sub n's like y. Ultimately, what's going to happen if I plot a bunch of points? What do you think is going to happen here? Yeah, and now these are discrete functions, by the way. You don't really connect them. Discrete meaning they're not they're not going to be continuous. It's just a bunch of dots, a bunch of it's like a scatter plot. No, not so much a scatter plot because it's not totally scattered. There's a pattern, obviously, right? But you can see that the dots are getting closer and closer to the x-axis. Hence, the output is getting closer and closer to 0. So we can treat this like a limiting case in a way. We can, even though we're not truly having continuity. So the sequence example is defined explicitly, right? Because we could explicitly find the 100th term. In other words, we can find the n term of the sequence by simply plugging the value of n, or whatever you need to do. There are a variety of rules which we can construct sequences, blah, blah, blah. We talked about rotating geometric already.
So let's look at example 2 now. Example 2. That's pretty obvious that's arithmetic, right? Because what are we doing over and over again? Adding 2. And then what are we doing over and over again for part B? Multiplying by -1/3 or dividing by -3, same thing, right? Okay, so that's just a review of stuff we've seen before. Now, let's talk about the limit of a sequence. And this is something that Ms. York cares a lot about because she will teach this to you guys next year in BC. The limit of a sequence and convergent divergence of sequence. So consider 1, 2, 3, 4, 5, and so forth, right? And it's defined explicitly as a sub n equals n. So our pattern is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so forth. That is our pattern. That's clear arithmetic. You're adding 1, right? And the formula would just be a sub n equals n, right? Because whatever n is, that's the output of the sequence. Now, what if I took the limit of that sequence as n approaches infinity? If I took a limit of this formula here as n approaches infinity, what does it become? What's the limit of n as n approaches infinity? Infinity. So we say this diverges. Diverge means to go away. Or to split. Go away from what? Or split from what? From certainty. Is infinity certain? No. Limits want certainty, right? So to go away from certainty or split from certainty. To go away or split from a finite number. Whereas convergence was mean it comes towards a number, right? So the limit exists. Does the limit exist for the example I just talked about? No, does not exist. Would it exist for, say, how about part B? So what's my formula here? It looks like if I write this as a general formula for part B, what's my first term? And what am I multiplying by over and over again? N minus 1, right? We talked about that. So if I were to take the limit of that sequence as n approaches infinity, what do you think it would converge to?
Sure, yeah. I mean, we can see intuitively it should, right? Even if it's alternate between positive and negative. But also just think about it. What if I raise -1/3 to a large exponent? That denominator is only going to keep getting bigger. Well, the numerator just goes back and forth between -1 and 1.
So yeah, so we would say that's 0. So this case, we'd say it converges in this case. And that's because it settles on a finite number. It's settling on something. And that's the whole point of today. To see whether the sequence will settle on something or doesn't. It doesn't say diverge, it does, it converges. That's all. So let's look at the definition. In the red box in the middle, definition limit of a sequence. We say that the sequence a sub n converges to a limit L if and only if the limit as n approaches of a sub n equals L, where L is a finite number, what I just said. If no limit exists, it diverges. If it increases without bounds, right? Just keeps going up, we say it diverges to infinity. Sometimes, just so you know, our limits may just go back and forth between a certain number. And we can't say anything about, like, for example, I'll do one more before we do the examples. But what if I had, let's just say that was my, my pattern. Just -1 to the n in purple. What does that mean, -1 to the n? What would be my outputs? -1, 1, -1, 1, -1, 1, -1, 1, 1, so forth, right? So if I were to graph that, it would just look like this, right? When n is 1, it's -1. Even though it's pretty consistent, I know I kind of threw it off a little bit. Even though it's consistent, can I really settle on just one number? I don't know. Is it certain? No, you need certainty for limits. So we'd say diverges in that case as well. But if I put a fraction next to it, like that, yeah, then it becomes an infinite geometric sequence where the ratio is between -1 non-inclusive. whenever the ratio is between -1 and 1, but not including -1 and 1, we could say it converges. And that's something that we'll just always can lean on for sequences. Okay. So I'm glad we're talking about this way because I didn't really talk about this way last year. So let's look at these examples here. So we're going to take an intuitive approach. We're just going to, I already did part C actually for you guys. Didn't realize it was there. But let's just write them out first, and then kind of think about the formula. So if I were to write the first 3 terms, what would my first 3 terms here be? Yeah, ... right? Here, this would be 2, 4, 8, ... This would be -1, 1, -1, 1, ... Cool? Okay, well, if I take the limit, sorry, what was that? Actually, let's think about here. Yeah, exactly. If I take a limit of this, right, that should actually converge. Right, that's because for because it does settle on a certain number. Yeah, sorry if I said it diverged. That should converge. But this one, that's gonna be infinity. That increases without bound. Meaning you can increase, but you have to eventually hit a limit or ceiling to say the limit exists. In this case, it does not. So we say it diverges. So this converges. That diverges. And this one here, if I take that limit, that does not exist. That's because it alternates. Between -1 and 1. So also we say this diverges. Because the odd and even terms kind of march their own beat, right? So you'll have the homework problems I hand out to you guys that looks like kind of like a vanilla type of sheet. They'll have those kind of problems for your practice. So okay, questions so far? No? Okay, we're doing great. We're about halfway through. Okay, let's look at some more. Okay, this one is interesting. Let's write the first 3 terms. You have 3/1, comma, what would the next term be? Next term. So I suspect that if I take the limit as n approaches infinity of that formula, that was a little loud. Okay. Enjoy your soda, whatever that is. Okay. If n gets really large,
Think intuitively, the top doesn't change, but the bottom does. Overall, we can say they're close.
yeah. And by the way, we've seen this before. This is not new. Isn't that a rational expression? Haven't we talked about limits of rational expressions as n approaches infinity? Horizontal asymptotes, right? This is just like a horizontal asymptote. Right? So we've seen this before. So this definitely converges. Does it 0 exactly? No. But that doesn't matter. That doesn't matter. Okay. Remember we talked about n factorial? It's n times n minus 1 times n minus 2 down to 1, right? So let's write some terms here. Great question. And I actually had a good explanation for this a long time ago, and I can't think of it right now. Yeah. I think because the pure definition of it is to multiply down to 1. Right, yeah, because if you have n is 0, right, it's 0. Just go with it for now. I have a good explanation. It's kind of like when you're racing to 0 power, it's 1, but I know why, because that's more because you don't have anything. Yeah, it's weird. Let me get back to you on that. Yeah, that's a great question.
Isn't my
Oh, you know what? We're starting at n equals 1 anyways, guys. But hey, we're starting at n equals 1, so don't worry about it. So what are my first few terms here? 1 over 1 factorial. 1 over 2 factorial. And I appreciate the challenge, Tom, so I'll come up with a good explanation for you by tomorrow. So you have 1, 1/2, 1/6, 1/24. I think you suspect what's going to happen. Those will probably converge, right? Yeah. Because if you take the limit. Yep. Or we'll see. No, actually, you can have a rational expression. What if I had what if I had 3n cubed plus 1 over n cubed? That would convert to 3. What if I had like 3n cubed plus 1 as my numerator and just n cubed on the bottom? Whenever the degrees were the same for a rational expression, that had a limit, right? So that would still converge. And actually, we saw in part A, the previous problem, that was 4. So this way, this will converge still. So really, we're just taking my kind of like a numerical approach. It's kind of the numerical what's happening. That's probably a good way of thinking about it. Questions so far? No? All right. And by the way, you will do way more complex stuff next year. We're just scratching the surface, but just get thinking about the mindset of what convergence, divergence, what that means. Convergence means the limit exists, divergence does not exist. That's terminology used often in sequences and series. Okay. Some other things to keep in mind, properties. We know our limit properties, right? Those same limit properties still apply when we're dealing with this stuff. Remember, if you're adding two sequences, you can take a limit of each of them separately by adding, subtracting them. If you have a constant multiple, you can pull constant multiple out. If you're multiplying, you can multiply the two limits. Dividing, you can divide, assuming the bottom limit's not 0. If you raise a power, you can take a limit of the sequence and raise the tap power afterwards. You guys remember squeeze theorem? Yep, that applies still. And we'll see it, I think, for one example here. If we're oscillating, which we have seen, you're kind of going back and forth, the ultimate getting closer and closer to 0. You could say 0. If you have an absolute value, it's all good. So let's talk about some of these common situations here. If you take a limit of a constant, that will converge. We saw that earlier with 4, right? That will converge. That converges to sorry, converge for all values. Actually, let me yeah, it converges to C. I don't know what to talk about. I mean, yes, of course it converges when n approaches infinity. It converges to C. Yeah. I don't know what to talk about. I don't know what converges for all n. Of course it converges. Here, this converges if A is between -1 and 1. Otherwise, diverges. It will diverge because you have the same number over and over again. Actually, well, no, it would be a constant multiple. Actually, then you know what? It reverts back. Let me take it back. Actually, no, you are right because it would the sequence itself, right, would converge. Let me take it back. Converges to 0. Let me take it back. Actually, think also can converge to a constant.
The German is the sequence, so wouldn't it just increase without bound? Like it's
We're not doing series. We're just doing the sequence.
No, I know, but n isn't like why would n be between -1 and 1?
I said A. A is between -1 and 1.
Oh, A.
A.
I don't know.
Yeah, sorry, let me fix this. Yeah, let's rest on this a little bit because we're getting a little kind of a little deep in the theory here now. I made it too simple. Definitely, this makes sense, right? That's like an infinite geometric sequence. We know this is true. It converges to 0. And also, it does converge to 1. If A is 1, then guess what? Every term is 1, right? So the infinite term would still be 1. But the negative one goes back and forth, as you saw earlier, right? It goes back and forth, it's alternating. So that would diverge. And of course, if A is bigger than negative, less than -1, it also diverges. So, okay. Now for this next one here, this will converge. Let's switch colors for a bit of contrast. This converges. If P is greater than 0. Because n is your base, right? Diverges if P is less than 0. Actually, let me rephrase that. Also converges if P equals 0. It converges to what? P equals 0. Just see. Because the bond will be 1. But diverges. That's because you'll have negative exponent. And what does it converge to if P is greater than 0? It would converge to 0, right? Why would this expression converge to 0? Because think about it. If n is like a bunch of positive integers, right? Like 1, 2, 3, 4, whatever. But if that is an exponent larger than 0, so let's say it's like 2, for example. If I raise like a million to the second power, great, it's a big number, but you can see over that number. You can see over a big number, which makes it small. Or even if it's a fraction, like a fourth root or fifth root, sixth root, it doesn't matter. It's still increased without bound on the bottom, but overall, the fraction is getting smaller, closer to 0. And then lastly, this one here diverges. Let's just rest this a little bit. Any questions at all? Again, just think about it. If your limits, sorry, if your sequence is just a constant, like okay, 4, then every term is 4. Of course, it converges to that number when you have the infinite term. Like, just what if you plug 1,000 for n? Well, there's nothing to plug in for n. 1,000 terms still 4. A to the n, if A is between A1 and 1, great. It converges to 0. If A equals 1 or -1, so if A equals 1, it converges to whatever to 1. But then when it alternates or diverges in the other cases, this one, if the exponent P is greater than 0, that will converge to 0. It also still converges to P equals 0, converges to whatever C is, then diverges in the other case. And then, of course, this diverges. Okay, questions? No? All right. Okay, last page. Ooh, this is a good one. Give me a sec here. I think what we're going to do, if I'm not mistaken, is take the natural log of both sides. Why? Just wait. Just wait. You guys remember your log properties?
Oh, yeah. And minus Ellen to that.
Okay. Okay. All right. So now, if you think about it, this is a little tricky. And of course, this still kind of came along for the ride. So what if I now take the limit?
Okay, so for you guys, cool limit properties.
For the second one, we should have just had that one too.
Wait, the second one.
The second one, we read.
In the limit,
Oh, I'm
I
sorry.
don't think there's.
Oh.
My bad. My apologies. Correct. There we go. Yeah. Okay.
We're okay with that? That's why I always check. I make mistakes. I don't know why I did that. We're okay with that?
Why don't you just like find the first 5 points?
You could do that, but we're trying to take a more algebraic approach.
We just say 2 to the n grows faster than.
It does, actually, it does. But if you think about it, what's this limit gonna be? Infinity, right? What's this one gonna be? Infinity as well, right? And what happens if it's subtract infinity? Comes zero.
Yeah. That's what comes zero. Yep. That's how you prove it analytically. Now, I do like the fact that you guys were thinking numerically from the beginning, right? Because yes, the top is getting big. The bottom's also getting big. But what's more powerful? A linear fact term or an exponential term? Exponential increases way more quickly. And now we can take a calculus approach as well, right? Think about tangent lines, right? What's happened to the tangent lines here? These increase way more quickly, right? These are way steeper than this, right? So we know this is increasing more in a more dominant fashion than the line level, right? So we would expect well, even though this converges, we do expect a separation between the top and the bottom. The bottom's increasing way more quick than top ever would. So ultimately, yes, numerically we could see that, but from an analytical standpoint, this is how you can prove it by approaching it this way, by using a log property. There's another rule too that involves derivatives, which it's called L'Hopital's rule. We're not there yet. You'll learn about it later. It's a cool derivative technique that you can apply to limits, but okay, let's move on to part B, and then part C, and then we're done for today. Okay, this one here, we're going to use the squeeze theorem.
Just like say that that one that was 0, like.
Yeah, ultimately what's going to happen, actually, I think it gets closer. Yeah, it's, well, I think that's when we said, with the limit n approaches, or x approaches 0. Oh, also for the approach to infinity, you're right. Yes, it is 0. You are correct, but we'll just do this anyway. We know this to be true, right? How do I know that to be true? What's the range for sine? Then 1 to 1, right? That's because we know this to be true. Okay. So what's the limit of n approaches infinity of -1 over n? What's the limit as n approaches infinity of 1 over n? So by squeeze theorem, the limit as n approaches infinity of sine n over n must also equal 0. And this will converge. So part A converges. I didn't really. And it also converges. Questions? No. So again, part A converges. Again, we do see, by the log properties as well as resin 2Tn is much bigger than n. And of course, here we do squeeze theorem. And the last one, I'll do blue here for a bit of contrast. So one thing you could do is you could just trying to think here because I don't want to confuse you guys too much. You could think of it like this. Now, even though this one alternates between -1 and 1, right? That's be -1 or 1. But guess what? You're always multiplying by what? Yeah, that's 0. So you get 0. Let me say this converges as well. Now, where things get a little messy is that what if this is 2 to the n over n squared plus 2? Then you have infinity times 0. And that's where we can't use this limit property. That's not for us to talk about. We won't have that discussion. That's for next year. But for now, just kind of keeping things simple. Here's what's happening. Take the limit, find the infinite term, see if it converges. Okay, so that covers all that stuff. So the homework I already shared with you guys. It's right here. You got a few minutes if you want to get a head start. I don't have an answer key for it yet. I'll make one later today. But you'll be doing kind of the same stuff here. So it should be more manageable. I'm not gonna send any of the hard problems because we meet again tomorrow. And I know there was prom over the weekend, so I don't want for GP to worry about that either. So yeah, that's all. And then we'll talk about series. Series really gets fun. We'll talk about series tomorrow. All right, we're all set.